For years, artificial intelligence operated under a strict limitation. It only spoke when spoken to. Algorithms sat idle in massive data centers, waiting for a human operator to input a prompt, press return, and command a single, isolated task. But over the course of a single 24-hour window, that passive call-and-response model was systematically dismantled. A synchronized wave of announcements from major tech hubs replaced it with something far more aggressive. Developers are now deploying agentic systems. Unlike standard conversational chatbots, an agentic AI is software engineered to think, spawn its own subworkers, and execute complex, long-term goals entirely without human intervention. This sudden shift toward autonomy triggered a geopolitical reaction. As these systems became more powerful, the struggle to control the underlying hardware intensified, leading to new trade blockades and an aggressive push for independent domestic chip production. To track how these parallel ecosystems are diverging, we have to tear down what engineers are calling the new autonomous stack, tracing the architecture from the high-level software layer all the way down to the physical microchips. At the top of this stack is the software. During a presentation to a global developer audience, Google rolled out Antigravity 2.0, a standalone application built around an agent-first architecture. This diagram illustrates how that architecture operates. Instead of one model answering prompt, a primary AI node dynamically defines the project, then simultaneously spawns 93 distinct subagents to handle code generation, asset design, and architectural planning in parallel. To test this, engineers challenged the platform to build a functional operating system core from scratch. The subagents worked continuously for a 12-hour window, generating 2.6 billion tokens to construct the core framework. The total computational cost for the entire build was less than $1,000. The demonstration grabbed the attention of the technical community when presenters attempted to boot up the classic video game Doom on the newly compiled operating system. Initially, the system crashed. The AI-generated OS simply lacked the necessary keyboard drivers to interpret player inputs. Instead of manually typing out a fix, the lead developer used a raw voice command, instructing the Antigravity system to write the missing drivers itself. The AI generated the required code, patched the operating system live on stage, and executed the game successfully. A process that previously required a team of engineers debugging a compiler bottleneck is now automated. The software layer can self-correct, can rapidly compile code, and execute vast frameworks in real time. Running hundreds of these autonomous agents in continuous asynchronous loops requires massive physical computing power. Specifically, it demands immense, uninterrupted memory bandwidth and video RAM. Knowing this, the United States had placed strict export controls on high-end hardware. Nvidia attempted to maintain its market access in China by engineering the RTX 5090D V2, a card explicitly degraded by a 25% reduction in memory bandwidth to bypass those US regulations. But the Chinese General Administration of Customs abruptly added the degraded card to its prohibited imports list, leaving Nvidia CEO Jensen Huang unexpectedly trapped by a sudden regulatory blockade while visiting Beijing. Shortly after the blockade, at the 2026 Alibaba Cloud Summit, the company revealed the Zhenwu M890 AI accelerator. This in-house silicon is engineered with a massive 144 gigabytes of memory, specifically to handle the high context window requirements of Agentic AI, providing a domestic alternative to American microchips. To scale this hardware, Alibaba rolled out the Panju AL128 SuperNode server. This diagram shows 128 discrete Zhenwu accelerators stacked into a single physical rack. Thanks to a proprietary interconnect switch operating with a 150 nanosecond latency, these 128 separate chips compute together as a single massive brain. Alibaba proved the viability of this domestic hardware by turning its own software loose on it. Their foundational model autonomously optimized a production-grade inference workload on the Zhenwu platform, running continuously for 35 hours and achieving a 10-fold speed improvement over the reference implementation. By pairing sovereign microchips with their own highly customized software, developers in the East are constructing a technology stack that functions independently of Western infrastructure. These parallel ecosystems are racing forward without unified global oversight, and that acceleration brings severe societal consequences. Speaking at the University of Oxford, Anthropic co-founder Jack Clark predicted that within 18 months, fully autonomous AI enterprises will be generating millions of dollars in revenue without human employees. His most critical prediction extends to late 2028. By that date, Clark warns that advanced AI systems will possess the capability to design and build their own successor models, permanently removing humans from the engineering loop. That timeline is backed by current capabilities. Anthropic's own Claude Mythos model has already demonstrated the ability to autonomously hunt down complex software vulnerabilities, chain together legacy bugs, and write functional zero-day exploits entirely without human instruction. Anthropic initially kept this model under strict access controls to prevent misuse, but that secrecy drew immediate political fire. U.S. lawmakers, including Representative Josh Gottheimer, forced Anthropic to end its secretive vulnerability hoarding, arguing that restricting threat data would leave smaller organizations defenseless against autonomous cyber attacks. The simultaneous rise of agentic software and sovereign hardware has moved the technology beyond the reach of traditional safety frameworks. As development cycles accelerate into autonomous loops, humanity is on a reactive trajectory, chasing systems that are beginning to outpace the speed of human decision-making.